Hello, everyone. In this section, we will introduce small signal analysis of BJT amplifiers, focusing on the common emitter amplifier. First, let us review the basic structure of a voltage signal amplifier. As shown in the figure, the system can be divided into three main blocks: the signal source, the amplifier, and the load. The purpose of a voltage amplifier is to amplify the voltage signal at the amplifier input, VI, and then deliver it to the output, VO. The small signal equivalent circuit of these three blocks is shown in the figure. The signal source can be represented by a Thevenin equivalent circuit. The amplifier has an input resistance Rin at its input side. At its output side, it can be modeled as a Thevenin-type output voltage source, where the input signal Vi is amplified by the open circuit voltage gain, AVO, and then delivered through the output resistance, Rout. The load is represented by the load resistance, RL. The input resistance of the amplifier, Rin, is defined as the input voltage signal, Vi, divided by the input current signal, II. From the equivalent circuit, Vi is obtained by voltage division between Rsig and Rin. Therefore, Vi equals Rin divided by the quantity Rin plus Rsig, multiplied by Vsig. This is important. The amplifier input signal is not the full source voltage Vsig. Part of the signal is lost across Rsig, so the amplifier can only amplify the portion that actually reaches its input terminal. After the input signal Vi reaches the amplifier input, it is amplified by the open circuit voltage gain, AVO. AVO is defined as the output voltage divided by the input voltage when the load is open-circuited, meaning that RL is infinite. In that case, the output voltage VO equals AVO multiplied by VI. So AVO is simply VO divided by VI under open-circuit load conditions. After finding Rin and AVO, we next calculate the output resistance, Rout. As introduced earlier, to calculate output resistance, we first set the input signal to 0. Then we apply a test voltage, Vx, at the output terminal and calculate the corresponding test current, Ix. The output resistance is then Rout equals Vx divided by Ix. From the equivalent circuit, when Vsig is set to 0, Vi also becomes 0. Therefore, the dependent output source, AVO times Vi, also becomes 0 and is equivalent to ground. In the simplified circuit, the test voltage Vx sees only Rout. Therefore, Vx equals Ix times Rout, and Rout equals Vx divided by Ix. After reviewing the amplifier equivalent circuit, the input voltage Vi is first amplified by AVO and then delivered to the load, RL. The load voltage VO is therefore AVO times Vi, multiplied by the voltage divider factor RL, divided by the quantity Rout plus RL. In other words, the amplified signal is divided between Rout and RL, so not all of the amplified output is delivered to the load. Some of it is lost across Rout. Now we can obtain the voltage gain provided by the amplifier, AV. It is defined as the output voltage VO divided by the input voltage VI, and it depends on the load resistance RL. Therefore, AV equals the open circuit voltage gain, AVO, multiplied by the voltage divider factor RL over the quantity Rout plus RL. Finally, we can calculate the global gain, also called the overall gain, from the source voltage Vsig to the output voltage VO. GV equals VO divided by Vsig, which can be written as VI over Vsig multiplied by VO over Vi. Therefore, GV equals Rin divided by the quantity Rin plus Rsig, multiplied by AV. All of these equivalent circuits are small signal equivalent circuits used for AC analysis. After reviewing the small signal equivalent model of a voltage amplifier, we now introduce the three basic small signal amplifier configurations formed by BJT devices. Please note that these are AC small signal configurations, not DC bias circuits. Since a BJT has three terminals, one terminal can be used as the small signal input, another as the small signal output, and the third terminal serves as the common terminal. This gives three possible configurations. If the base is used as the small signal voltage input, the collector is used as the small signal voltage output, and the emitter is the common terminal. This configuration is called the Common-Emitter configuration, or CE amplifier. If the emitter is used as the small signal voltage input, the collector is used as the small signal voltage output, and the base is the common terminal. This configuration is called the Common Base configuration, or CB amplifier. If the base is used as the small signal voltage input, The emitter is used as the small signal voltage output, and the collector is the common terminal. This configuration is called the Common Collector configuration, or CC amplifier. We first analyze the CE amplifier. As shown in the figure, the signal source Vsig and the source resistance Rsig are connected to the base terminal of the BJT. The load is connected to the collector terminal, and the voltage across the load is the output voltage, VO. The part between the signal source and the load is the amplifier circuit itself. Therefore, the amplifier circuit is the part enclosed by the red dashed line. For this amplifier, the input terminal voltage is Vin. The resistance seen looking into the input terminal is the input resistance Rin, and the resistance seen looking back into the output terminal is the output resistance Rout, as labeled in the figure. Next, we replace the BJT with its small signal equivalent circuit. Since the emitter is directly grounded, the pi model is more convenient here. The blue part of the circuit represents the BJT small signal model. The resistance Ro represents the contribution of the early effect. If the early effect can be neglected, then Ro is treated as infinite and can be removed from the circuit. We first find the input resistance Rin. From the small signal equivalent circuit, the only resistance seen looking into the amplifier input is Rpi. Therefore, Rin equals Rpi. We can also see this from the definition. Rin equals the input voltage Vin divided by the input current In. Since Vin is VBE and the input current is IB, VBE equals IB times Rpi, so VBE divided by IB equals Rpi. After obtaining Rin, we can calculate the input voltage Vin. It is given by the voltage divider between Rsig and Rin, so Vn equals Rin over the quantity Rin plus Rsig multiplied by Vsig. Since Rin equals Rpi in the CE amplifier, Vn equals Rpi over the quantity Rpi plus Rsig multiplied by Vsig. Here, Vn is also the small signal voltage VBE. Once VBE is known, the controlled output current is Gm times VBE. This current flows out of the output node through the equivalent parallel combination of Ro, Rc, and Rl. Therefore, the output voltage is negative Gm times VBE multiplied by the parallel combination of Ro, Rc, and Rl. The negative sign indicates the phase inversion of the common-emitter amplifier. After finding VO, the voltage gain of the amplifier is AV equals VO divided by Vn. Since Vn is VBE, AV equals negative Gm multiplied by the parallel combination of Ro, Rc, and Rl. The open circuit voltage gain, AVO, is the voltage gain when RL is infinite. Under that condition, the load branch is open, so AVO equals negative Gm multiplied by the parallel combination of Ro and Rc. Finally, the global gain GV can be found by multiplying the input voltage divider factor by the amplifier voltage gain. Therefore, GV equals Rin over the quantity Rin plus Rsig multiplied by AV. For this CE amplifier, this becomes negative Rpi over the quantity Rpi plus Rsig multiplied by Gm and by the parallel combination of Ro, Rc, and Rl. Next, we calculate the output resistance Rout. To do this, we set the input signal to 0 and apply a test voltage Vx at the output terminal. Then we calculate the test current, Ix. Remember that Rout is an internal output resistance of the amplifier, so the load resistance RL is not included in this calculation. After substituting the BJT small signal model, we can see that the input voltage is 0. Therefore, the controlled current source at the output side is also 0 amps, which is equivalent to an open circuit. As a result, the output side equivalent circuit only contains Ro and Rc. These two resistances are in parallel. Therefore, Ix equals Vx divided by the parallel combination of Ro and Rc, and the output resistance Rout equals Vx divided by Ix, which is the parallel combination of Ro and Rc. To summarize the CE amplifier, the input resistance is Rpi, the open circuit voltage gain is negative Gm times the parallel combination of Ro and Rc, the output resistance is the parallel combination of Ro and Rc, and the global gain includes the input voltage divider factor Rpi over the quantity Rpi plus Rc multiplied by the loaded voltage gain. As discussed earlier, a good voltage amplifier should have a high input resistance so that less of the source signal is lost across Rsig. However, the input resistance of the basic CE amplifier is only Rpi, which is a moderate resistance and not very high. This is one drawback of the CE amplifier. Also, its open circuit voltage gain is negative, meaning that the output signal has a 180-degree phase shift relative to the input signal. Because the input resistance of the basic CE amplifier is not high enough, we can improve it by adding a resistor RE at the emitter terminal, as shown in the circuit. Adding this emitter resistance greatly increases the input resistance seen at the base terminal. Again, we replace the BJT with its small signal equivalent model. Since the emitter now has the resistor RE, the T model is more convenient. In this analysis, we first ignore the early effect resistance RO. The analysis of a small signal amplifier usually starts by finding the input resistance, Rin. Rin equals the input voltage Vin divided by the input current In. At the input terminal, In is the base current IB. Also, IB equals the emitter current IE divided by 1 plus beta. The emitter current IE is Vin divided by the quantity Re plus Re. Substituting this into the expression for Rin gives Rin equals the quantity Re plus Re multiplied by 1 plus beta. This is the resistance reflection rule. An emitter side resistance can be reflected to the base side by multiplying it by 1 plus beta. Since the quantity 1 plus beta times Re is R pi, the input resistance becomes R pi plus 1 plus beta times Re. Compared with the basic CE amplifier, adding Re increases the input resistance by 1 plus beta times Re, which is a large increase. After Rin is found, the input signal is Vin equals Rin over the quantity Rin plus R sig multiplied by V sig. The emitter current is then IE equals Vin divided by the quantity Re plus Re. This emitter current can be converted to the output side current because IC equals alpha times IE. Once the output side current is known, the output voltage can be calculated. The output voltage VO equals negative IC multiplied by the parallel combination of RC and RL. Since IC equals alpha times IE, this becomes negative alpha times Vn over the quantity Re plus Re multiplied by the parallel combination of RC and RL. From the expression for VO, the voltage gain is AV equals VO divided by Vin. Therefore, AV equals negative alpha times the parallel combination of RC and RL divided by the quantity Re plus Re. The open circuit voltage gain, AVO, is obtained by removing RL, so AVO equals negative alpha times RC divided by the quantity Re plus Re. The global gain is GV equals VO over V sig, which is Vn over V sig, multiplied by VO over Vn. Therefore, GV equals Rn over the quantity Rn plus R sig, multiplied by AV. In this circuit, that becomes negative Rn over the quantity Rn plus R sig, multiplied by alpha times the parallel combination of RC and RL, divided by the quantity Re plus Re. Next, we find the output resistance, Rout. As usual, we set the signal source to 0. When V sig is 0, Vin is also 0, so IE is 0. Therefore, the controlled current source at the collector is 0 amps and is equivalent to an open circuit. The test voltage Vx applied at the output sees only RC, so Rout equals RC. The load resistance RL is not included when calculating the amplifier output resistance. Now let's summarize the difference between a CE amplifier without RE and one with RE. Adding RE increases the input resistance by a factor related to 1 plus GM times RE. More specifically, Rin becomes approximately R pi multiplied by the quantity 1 plus GM times Re. However, the open circuit voltage gain decreases by roughly the same factor. Therefore, when using Re in amplifier design, we must consider the trade-off between a higher input resistance and a lower open circuit voltage gain. In summary, the emitter resistor Re increases Rin by the factor 1 plus GMRE, but it also decreases AVO by the same factor 1 plus GMRE. Because the voltage gain is reduced, the allowable input signal range for linear amplification increases by approximately 1 plus GMRE. This idea was introduced earlier when we discussed amplifier saturation. Lowering the gain increases the input range over which the amplifier can remain linear. Adding Re also improves the frequency response of the circuit, and we will discuss that later in the frequency response chapter. In addition, Re provides negative feedback and helps stabilize the circuit. For example, if an external disturbance causes IC to increase, then IE also increases. The larger IE produces a larger voltage drop across Re, which raises the emitter voltage VE. This reduces VBE, and because IC depends exponentially on VBE, the collector current is pulled back down. In this way, RE stabilizes the operating point. Finally, using the CE voltage amplifier as an example, let us summarize the standard procedure for analyzing a voltage amplifier. Step 1 is to find the input resistance Rin, because this tells us what fraction of the source signal Vsig reaches the amplifier input as Vin. For BJT voltage amplifiers, the input terminal is usually either the base or the emitter, so the resistance reflection rule is very useful. Step 2 is to calculate Vin. Step 3 is to find the relation between the input voltage and the output side current, usually by solving for IB or IE, using a pi model or T model. Step 4 is to convert that current into the current entering or leaving the output node. Step 5 is to use the output current and the output side resistances to calculate VO. Step 6 is to obtain the voltage gain AV, the open circuit voltage gain AVO, and the global gain GV. Finally, set the input signal to 0 and apply a test voltage at the output to calculate Rout. This is the general logic for analyzing a single-stage voltage amplifier. That concludes the introduction to small signal analysis of BJT amplifiers, focusing on the common-emitter amplifier. Please stay tuned for the next lecture. See you next time. Bye-bye.